Hello everyone, I am Ms. Kruti Jai Pancholi, Assistant Professor in LG Institute of Engineering and Technology in Department of Electronics and Communication. This video is about subject Microwave Engineering. We are going to start the unit Analysis of Microwave Transmission Line and Waveguide. In this video, you will learn about standing wave and standing wave ratio, voltage standing wave ratio, efficiency of transmission line, losses due to impedance mismatch. In the last video, you learned about the term characteristics impedance. The characteristics impedance is the impedance at which reflection would not occur. So when the line is terminated with its characteristics impedance, then there is no impedance mismatch, and if there is no impedance mismatch, there will not be any reflected energy from the load. Whereas the load is not connected with the perfect characteristics impedance, some energy that is reflected back, and thus the incident and the reflected energy along the length of the line is that forms the standing wave. So here the standing wave is formed when the incident wave gets reflected. The standing wave which is formed contains some voltage. The magnitude of the standing wave that can be measured in terms of the standing wave ratio. The equation for the voltage standing wave ratio is S is equal to V max upon V min, and the value of the S that is between 1 and infinity. So it is the ratio of maximum voltage to the minimum voltage in a standing wave that can be defined as voltage standing wave ratio. It can be also find it out in terms of the reflection coefficient, because here we have the incident wave and the reflected wave. So VSWR that describes the voltage standing wave pattern that is present in the transmission line due to phase addition and subtraction of the incident and the reflected wave. So here we have the one formula in terms of the reflection coefficient. S is equal to 1 plus rho upon 1 minus rho. Similarly, if the VSWR is given to us, we can find out the reflection coefficient rho. The larger the impedance mismatch, the higher will be the amplitude of the standing wave, because when you are transmitting the power or the voltage from the generating end, now if the characteristics impedance that will not match, then some power that is absorbed by the load and other power that is reflected back to the source. So at that time the amplitude of the standing wave that is higher, and therefore if the impedance is matched perfectly, then V max gem V minimum is equal to 1 gem 1. Hence the value for the VSWR is unity, which means the transmission is perfect. So this can be asked in the Viva also. What should be the value of the VSWR ideal value? Then it is the unity for the distortionless transmission. The parameter to find it out the efficiency of the transmission line, it is said as the efficiency of transmission line. It is denoted by the eta, and it is the ratio of the power delivered at the reception divided by the power sent from the transmission end, and efficiency, so it is multiplied by the 100. So this way we can find out efficiency of transmission line. whenever there is no impedance mismatch, so some losses would occur in the transmission line, and that are attenuation loss, reflection loss, transmission loss, return loss, insertion loss. So these all are the measurement parameter. From finding these all parameters, we can have the idea about the transmission line. First is attenuation loss. So when the signal is transmitted from the transmitting end, some part of the signal that is the absorbed in the transmission line, so that it is known as the attenuation loss. So the loss that occurs due to the absorption of the signal in the transmission line is termed as a attenuation loss, which is represented as attenuation loss. We are measuring this loss in the dB. It is equal to 10 log 10 EI minus ER upon ET, where EI is the input energy, ER is the reflected energy from the load to the input, and ET is the transmitted energy to the load. Next is the reflection loss. Reflection of the signal due to the impedance mismatch is referred to as a reflection loss. So the loss that occurs due to the reflection of the signal due to the impedance mismatch of the transmission line is termed as reflection loss. Reflection loss is measured in the dB. It is equal to 10 log 10 EI upon EI minus ER. EI is the input energy, ER is the reflected energy from the load. Next loss, transmission loss. So the loss that occurs while transmission through the transmission line, is termed as transmission loss. So which is represented as transmission loss is equal to 10 log 10 EI upon ET. So what is the input energy and the ratio of input energy to transmitted energy is referred to as a transmission loss. Return loss. The measure of the power reflected by the transmission line. Again, it is very important parameter in the microwave, that the power reflected by the transmission line, that is, can be find it out by finding out the return loss. So return loss in dB is equal to 10 log 10 EI upon ER, where EI is the input energy and ER, that is the reflected energy. Insertion loss. The last loss due to the impedance mismatch is the insertion loss. The loss that occurs due to the energy transfer using a transmission line compared to energy transfer without the transmission line. So when you use the transmission line and without the transmission line, whatever the power that transfer through the transmission line is referred to as a insertion loss. So even is the energy received by the load when directly connected to the source. When directly connected to the source and load are directly connected without the transmission line. And what is the E2? When the transmission line is connected between the load and the source. So at that time, the loss that we can find, it is the insertion loss. So in this video, we learned about. Now we are doing the program in MATLAB for the concepts which we studied. A lossless transmission line of Z0, that's a characteristics impedance, equal to 100 ohm, is terminated by an unknown impedance. The termination is found to be at a maximum of voltage standing wave ratio, and the VSWR is phi. what is the value of terminating impedance? The solution, here the value is given to you, that is Z0, SWR is denoted by S, and we need to calculate the ZL or the Z1. The MATLAB code for this, that is the Z0 is equal to 100, characteristics impedance in ohm, S is equal to 5, voltage standing wave ratio. Calculation, that is Zm is equal to Z0 multiplied by S. So Z1 is equal to Zm. So the output we can print it. Okay. Using this you can find out the terminating impedance at a maximum of voltage standing wave is Z1 is equal to percentage 3.0 F float value, and the ohms, that is the Z1. You can run this code in the SCI lab also. So answer you will get, it is Z1 equal to 500 ohm. The second program or the example, a typical transmission line has a resistance of 8 ohm per kilometer, impedance of 2 millihenry per kilometer, a capacitance of 0.02 microfarad per kilometer, and a conductor of 0.07 microsiemens per kilometer. Calculate the characteristics impedance, attenuation constant, phase constant of the transmission line at a frequency of 2 kHz. If a signal of 2 volt is applied and the line terminated by its characteristics impedance if the line is 500 km. So here the values given is R is equal to 8 ohm per kilometer, inductance 2 millihenry per kilometer, C is equal to capacitance is equal to 0.02 microfarad per kilometer, G is equal to 0.07 microsiemens per kilometer, F is frequency is 2 kHz. You have to find out the characteristics impedance. Attenuation constant is alpha, phase constant is beta, and power delivered to the load, that is the P, or you can denote it by PL. As we know that the gamma, that is the propagation constant, and this propagation constant is equal to the alpha plus J beta. So alpha is attenuation constant and beta is the phase constant. MATLAB code. The given values we always write, R is equal to 8, L is equal to 0.02. It is the inductance of the transmission line in the Henry per kilometer. Capacitance C is equal to 0.002 multiplied by 10 raised to minus 6. G is 0.07 multiplied by 10 in raised to minus 6. That's a conductance in a Siemens per kilometer. F is 2 kilohertz, it is 2000. Now we need to put the value of the omega. So we are finding out using the omega is equal to 2 into pi into F. Voltage, input voltage Vs is equal to 2 voltage, and length of transmission line in kilometer is 500. So now the calculation for the Z0, it is the square root of R plus j omega L upon G plus j omega C. The real part of the Z0, that is X, and the real part of the imaginary part of the Z0 is the Y. So now the characteristics impedance of the this particular line, that is the Z0, and we can also find out the propagation constant gamma. Gamma is equal to square root of Y into Z. So we can put the value of the Y and Z. What is the Y? G plus j omega C. And what is the Z? It is the R plus j omega L. So gamma is equal to alpha plus j beta. So real part of the gamma, that is attenuation constant, and imaginary part of the gamma, it is the phase constant. We need to find out the power. Okay, so very first we want to find out the current, so we have find it out the load current. It's a V upon Z, and we can find it out the power delivered to the load. It is this P into I square R. Okay, and we can find it out the value of the attenuation constant. The um, the attenuation constant unit is Newton per kilometer. Phase constant, power delivered to the load. So it is about the MATLAB code for the two programs. You have to run this program in the MATLAB for the practice. Thank you very much, everyone. This is the output of the example, that is A is equal to 0.0387 Newton per kilometer, B is equal to 0.025 43 43 radian per kilometer, P is equal to 72.1 micrometer. You can consider these as an example as well as the practical purpose. How can we find out using the MATLAB? Thank you very much, everyone.